Imagine sending a simple message across the internet. Just one click and boom, it is gone. But have you ever wondered what actually happens behind the scenes? Good day, we are the students of BSCPE3GF, and for today's video, we invite you to follow the journey of a packet as it travels through a network. Think of it as a digital traveler moving from one device to another, changing paths, and making important stops along the way. In this presentation, we will clearly and systematically explain what happens to a packet as it traverses from a PC to a server, and then makes its way back again. From address changes to routing decisions, we will break down each step so the process becomes easy to understand. So sit back and let us take you through the invisible yet fascinating route that every packet takes to deliver information across the networks.
Now, let's proceed to the network overview. In our Cisco packet tracer setup, we have one PC, two routers, two switches, and one server. The PC is on a private network while the server is on a different network, simulating communication over the internet. This communication follows the OSI model, where the layer 4, or the transport layer, handles the port. Then we have the layer 3, or the network layer, handles the IP addresses. And lastly, we have the layer 2, or the data link layer, which handles the MAC addresses.
Step 1. Packet creation at the PC. So let's start at the PC where the communication begins. At this point, we focus on the IP addressing at layer 3, which identifies the source and the destination of the packet. And based on our configuration, the PC has a private IP address of 192.168.1.100. When the PC sends data, it assigns this address as the source IP of the packet. In addition, the application running on the PC is assigned a source port number, which is randomly generated ephemeral port. So in this case, the source port is 54321. Then, the destination IP address is the server's public IP, which in our scenario is 142.250.72.78. Since the communication is using HTTPS, the destination port number is 443, indicating secure web traffic. These port numbers belong to layer 4, which is the transport layer. The combination of the source IP address and source port number, that is 192.168.1.100 and 54321, forms what is known as a socket. A socket uniquely identifies an application process on a host within a network. To summarize the first step from PC to router 1, the PC encapsulates the data with its private IP address as the source, the server's public IP address as the destination, an ephemeral source port, and a destination port of 443 for HTTPS. This complete socket information allows the packet to be correctly forwarded to the next device, which is the router 1. Now, let's proceed to the step 2, which is MAC addressing and ARP.
Now, let's proceed to step number 2, the MAC addressing and ARP. At this stage, the packet is being sent from the PC to router 1, which is the first hop in the network. Before the packet can be transmitted on the local network, the PC must determine where to send it at layer 2. Because the server is not on the same local area network, the PC knows that the packet must be forwarded to its default gateway, which is router 1. To do this, the PC uses the Address Resolution Protocol or ARP. ARP allows the PC to discover the MAC address of the router associated with the default gateway's IP address. Once ARP resolution is complete, the PC prepares the layer 2 or the data link layer information. We have here the source MAC address, destination MAC address. The destination MAC address is set to routers 1's MAC because it is the next hop and the first device that will receive the packet on its way to the server. Finally, the packet already containing the IP addresses and port numbers is encapsulated into an Ethernet frame using these MAC addresses and is then transmitted from PC to router 1.
For the step 3, we have NAT and PAT at router 1. When the packet reaches router 1, an important process takes place before it can be forwarded to the public network. Router 1 performs Network Address Translation or NAT and Port Address Translation or PAT. This is necessary because the packet originated from a private IP address, especially 192.168.1.100. Private IP addresses are not routable on the public network, meaning they cannot be used outside the local network. Through NAT, router 1 replaces the private source IP address of the packet with the router's public IP address. This allows the packet to be recognized and routed across the internet. At the same time, PAT modifies the source port number. This enables router 1 to keep track of multiple internal devices communicating with external servers using a single public IP address. Each connection is uniquely identified using different port numbers. As a result of NAT and PAT, the source IP changes from the PC's private IP to the router's public IP, and the source port may also be changed to ensure uniqueness. This translation allows the packet to safely and correctly continue its journey toward the server on the public internet.
NAT table. Router 1 stores this mapping in its NAT table so it knows how to forward the reply later. And the MAC address update. At every hop, MAC addresses always change. The packet is forwarded to router 2.
Now, we have the step number 4, router 2 to server. Next, the packet travels from router 2 to the server, wherein at this stage, no network address translation is performed by router 2. The packet is already using public IP address, so it can be routed normally across the internet. So, what stays the same? The layer 3 network or the layer 4, which is the transport layer information, remains unchanged. In here, you can see that these are the source IP address, destination IP address, source port, and the destination port. These values remain constant because they identify the original sender and the final destination of the packet. Now, if you are wondering, what changes? Only the layer 2 or the data link layer information changes as the packet moves to the next hop. These are the source MAC address and the destination MAC address. The source MAC is updated to router 2's MAC, while the destination MAC is set to the server's MAC because the server is now the next and final hop. Once these MAC addresses are updated, the packet is encapsulated into the Ethernet frame and delivered to the server. Packet arrival at the server receives the packet, processes the request, and prepares to send response back to the PC. This response marks the first time the server initiates communication back to the client. To do this, the server creates a new packet. In this packet, we have first the source IP address, which is the server's own IP address indicating where the response originates. And then the second one is the destination's information, which will correspond to the client's connection and will be explained in the next step as the packet travels back to the PC.
For the step 5, we have server trace and reply. After receiving the request, the server prepares a response. In the response packet, the source IP address is the server's public IP, or the 142.250.72.78. Since the data is coming from the server, the destination IP address is 203.0.113.5, which is the public IP of the PC's network assigned through NAT. This allows the response to reach the correct router that represents the PC on the internet. For the port numbers, the source port is 443, indicating HTTPS traffic from the server, while the destination port is 61,000. This destination port was assigned earlier during the initial connection and allows the router to correctly map the response back to the PC. Layer 2. The source MAC address is the server's MAC address, and the destination MAC address is router 2's MAC, since the router is the next hop on the return path. The packet is then encapsulated into an Ethernet frame and sent back toward the PC through router 2.
Step 6. Message goes back to PC. Now, we will be discussing on how the packet traverses back from server to PC. Because of the port address translation, the destination port in the response is still a public port. This allows the routers to correctly track the connection and forward the packet back to the correct network. So first, from router 2 to router 1. In here, we have the router 2 back to router 1. As the response packet reaches router 2, it is forwarded toward router 1, which is the router of the PC's network. At this point, the IP addresses and port numbers remains unchanged because the IP addressing provides end-to-end delivery and identifies the correct application on the destination device. So what changes again are the MAC addresses. The source MAC becomes router 2's MAC address and the destination MAC is set to router 1's MAC address since router 1 is the next hop. Next is from router 1 to PC or NAT reversal. Now, when the packet arrives at router 1, NAT and PAT come to play again, but this time in reverse. So when router 1 checks its NAT table, where it previously recorded the mapping between the public IP and port number and the PC's private IP and port, using this record, the destination IP is translated from 203.0.113.5 back to 192.168.1.100 and the destination port is translated from 61000 back to 54321. After this translation, the MAC addresses are updated one final time. The source MAC became the router 1's MAC address and the destination MAC became the PC's MAC address. The packet is then encapsulated and delivered to the PC, where the correct application receives the data. And that completes the journey of the packet from the server back to the PC.
In summary, we have the following. First, IP addresses identify devices for end-to-end communication. Next, port numbers identify the specific applications involved. Third, MAC addresses change at every hop to deliver the packet to the next device. And finally, NAT and PAT allow private devices to communicate over public networks. This entire process follows the OSI model and the encapsulation principles discussed in our Computer Networks module. Once again, we are the students of BSCPE 3GF. We are Jane Arian Gaela, Francer Ruiz Talantad, and Glyza May Toque. And this presentation explained what happens to the packet as it traverses from a PC to a server and back again. Thank you.